Williamson synthesis, what happens is, the basic reaction is you take an alkyl halide, make it react with alkoxide. Oxygen pe always negative charge, sodium has positive charge. You get ether. So let's make this R dash, this will be R dash, and NaX is precipitated out. Okay. So the mechanism of this particular reaction, this is also an SN2 reaction. You can see the nucleophile O minus has lots of negative charge. So this is the nucleophile which attacks your alkyl halide. So Rx halide is electronegative, pulls on the electrons. So this particular carbon has a slight positive charge, which is ideal for the nucleophile to attack. So this also SN2 attack of nucleophile, alkoxide, which is the nucleophile. On primary alkyl halide. Yeah. Another advantage with this particular method is, so any kind of ether can be prepared, even secondary and tertiary ethers you will get from this method. Symmetrical, asymmetrical, unsymmetrical, all types of ethers. But it's not exactly a catch, but one thing to note is that any ether can be prepared, but your alkyl halide should be primary only, because again, because the mechanism is SN2 attack, right? So to make it ideal for SN2, if you don't want to end up with an elimination wala product, the alkyl halide needs to be primary. So in case you want like a secondary tertiary thing, your alkoxide ion can be anything. Like this R dash can be either secondary or tertiary, but the alkyl halide always needs to be primary to make it ideal or suitable for SN2 attack. Okay, that's the main point here. The mechanism is same because we are talking about alkyl halides here. So पीछे से, so the alkoxide, sodium alkoxide जो भी है, this nucleophile O minus, let's say we have RCH2X. So this particular thing attacks this as this thing leaves. So you have that intermediate product that you associate with SN2. This is the intermediate. You have R dash O. As the bond is forming here, this bond starts breaking. And yeah, finally the splits, leaving group leaves, attacking group bonds. So you get R dash O CH2R plus X minus. The nucleophilic SN2 mechanism that you're familiar with.
How many mechanisms are there in this chapter?
I don't have a count of it, Kaveri, I'm not sure. But if you remember the basic, like this is same as what you learned in haloalkanes, haloarenes. This is SN2 mechanism, just that you're applying for preparation of ether, this particular case. Oh, Sia has disappeared.
So this is one type of mechanism, but also there's the protonation, deprotonation wala is another type. Different mechanisms SN2 only.
So SN2 is substitution nucleophilic. So when the attack of the nucleophile happens is SN2. So the nucleophile is suppose is a carbon atom. The attack of the nucleophile and the leaving group leaving takes place at the same time. So that is the main thing about SN2. So बीच में nucleophilic attack वाला है ना that particular step. तो वहाँ पे that's the SN2, like in the same step water leaving is also happening, the other alcohol being attached is also happening. So that's
The intermediate.
the second step. Yeah, वहाँ पे you
But
find the intermediate.
how is this different from the protonation attack, deprotonation thing that we did?
It's the same, that just has extra steps, like for the nucleophile to attack, like protonation also takes place. That's how that OH can be removed as H2O easily. The main nucleophilic attack जो हो रहा है follows SN2 there also, here also. Yeah. So main points with this, any ether can be prepared. Just choose the right reactants.
Ma'am,
Hmm?
I got disconnected. Can you explain this blue line, the last one?
This is the mechanism. Like, see, haloalkanes, haloarenes, maybe when you were introduced to SN2, this is what you learned, right? So nucleophile attacks from the backside. So as this bond is being formed, leaving group के साथ जो bond है, that starts getting weaker. So this is like your unstable intermediate. So it happens in one step that nucleophile is forming a bond with this while the leaving group leaves. So this is the final product you get, your ether. Yeah.
And what have you written? Any ether can be prepared.
So previous method ke saath, the limitation was that you needed to do it with primary alkyl ethers only. Like agar ek side secondary or tertiary chahiye, to that's not possible because then it's going to take the elimination route. So you don't have that problem here as long as you choose the correct reactant. So if you want a secondary or a tertiary alkyl group wala ether, just pick that particular alkoxide. Only your alkyl halide needs to be primary.
Wait, I didn't understand. Why did that have to be primary, the previous one?
For the previous one, so previous one that needed to be primary because if you took tertiary or secondary, then you won't get SN2 mechanism with that. Then that's because that takes place with SN1 mechanism.
Yeah.
This thing, yeah. That's the thing. Elimination. Okay. Here also that's the case, which is why only your alkyl halide needs to be primary. Taki this particular mechanism can take place. So if you want to prepare secondary tertiary, then you can choose that particular alkoxide ion. So, okay, so I'll just put that write that down in words. So the features with this, if you use a primary alkyl halide RX, this is the best case, ideal scenario. You'll get what you want properly. If you use a secondary alkyl halide, you may still get your ether, but the yield won't be that great. So it's not ideal. It's pretty iffy. Like it's not like 100% confirmed ki your end product will be ether. There's a chance, depending on the reaction condition, you may get an elimination product also. And if you take tertiary alkyl halide, this is outright, you will not get ether because this will always go the route of SN1 and then you'll end up getting an alkene. Okay. And the reason for this happening is that, so in the case of secondary and tertiary alkyl halides, So one, you have steric hindrance, which because of which you can't guarantee ki SN2 mechanism will take place. There is a possibility for SN1. Also, the fact that the alkoxide ion jo hai, the nucleophile, is a strong base, which is a factor in elimination reactions. Like elimination kaise ho raha hai? The strong base attacks, like takes that H plus and that triggers that elimination, right? So because of these two reasons, with secondary and tertiary alkyl halides, uh, they're like tertiary though you will definitely not get an ether, ends up with elimination product. Secondary, it's a little iffy, like you need to be very careful with the polarity and what like how big of a compound you're taking and all that. It's not ideal. So if your like alkyl halide is primary, that is the ideal case, you will end up with an ether. ठीक है. So ether mein, this is the main thing with respect to preparation. It also gives you, it's like a lot more clarity on the difference between elimination versus substitution. When do you get what product and what are the factors? Like how do you decide ki substitution hoga, ki elimination hoga? All of those things. Things that you need to take note of. Okay. Other two methods of preparation are like tiny, it's just basic, just one step reactions. I'll just give it to you, note it down. So let me know once you're done with this, then we'll look at the other ones.
But so even tertiary is not ideal, right?
No, that's why I said not ideal. Like you won't get ether, no ether. You
Yeah.
get a so I'll just make it more clear. Uh, Reasons why tertiary and secondary alkyl halides are not preferred or are not used. Steric hindrance will not guarantee SN2 mechanism, and RO being a strong base also will not guarantee, like that will push the reaction towards elimination. So the consequence of this is that elimination is preferred over SN2. That's the main thing. These two, elimination is preferred.
I didn't understand the part about RO being a strong.
So the whole, like if you recall elimination, elimination mechanism, what triggers it is that you have a strong base attacking the beta carbon.
Yeah, like alcoholic here.
Yeah. So RO minus is a strong base. So that will, like if you have a stable carbocation ka possibility, so steric hindrance, so because of steric hindrance, SN2 is not as stable as carbocation. So if this had to choose ki, acha, should I go this route or this route, it's going to prefer a more stable route. So it's going to go with elimination rather than SN2 mechanism or a substitution mechanism.
I didn't understand.
So like you remember elimination ka mechanism, right?
Yeah.
And a strong base is required to trigger elimination ka mechanism.
Yeah, because strong bases will attract the hydrogens.
Yeah. So in this case, attracting that hydrogen is going to produce a tertiary carbocation, which is more stable. So if that strong base is there, rather than going this route, it's going to go take the elimination ka route, which is why tertiary is not preferred in this.
But why not in primary?
क्योंकि primary carbocation is not stable, right? Like this is pretty straightforward. पीछे से
Yeah.
करेगा, rather than take a hydrogen here, it will form a bond with carbon and the leaving group leaves. That was the fundamental difference between SN1 and SN2. Why primary goes with SN2 and why tertiary will go with SN1. That's what we're discussing here. Why this is primary is ideal, but not with secondary and tertiary. तो अगर सेकेंडरी टर्शरी है तो एलिमिनेशन होगा. क्यों एलिमिनेशन होगा? Because you have RO being a strong base and steric hindrance is going to prevent the SN2 mechanism. मतलब ether नहीं मिलेगा.
But ma'am, for strong base, like elimination, that can happen with primary also.
So there are multiple possibilities, right? So RO being a strong base is one thing. It is also a nucleophile because it's got negative charge and it's attracted to positive charge. So always it is not like, if you observe all these mechanisms, it's literally negative charge being attracted to positive charge or positive charge attracting like a pair of electrons or getting attached to a pair of electrons, lone pair of electrons or whatever, right? So there's always multiple routes that a reaction can take. Which route it's going to take will also depend on other factors. So that's what I'm discussing here. Ki primary alcohol, like primary alkyl halide hai, elimination can take place, but also this can take place. Same is the case with tertiary also. It can get attracted to the carbon or it can get attracted to the hydrogen attached to the carbon. But in the case of tertiary, like if this nucleophile has to attach itself to the carbon, now this carbon atom is attached to more carbon atoms. That's going to make it more difficult. So it would rather attack a hydrogen which is on the outside and trigger the elimination reaction. And in the case of primary, it doesn't have that steric hindrance, plus attacking a hydrogen on the outside, creating that carbocation, like which is not really that stable also. So it would much rather go ahead with SN1 mechanism.
I understood the part about there being more steric hindrance in secondary and tertiary, and that the fact that RO is a strong nucleophile, that I got. But strong base ka I didn't understand. The strong nucleophile kind of,
What did you not understand about strong base?
like, okay, it's attracting hydrogens, but that can happen in both primary and secondary tertiary, right?
Yeah.
I understood that the carbon in secondary and tertiary would be attached to more carbon, so it would be harder for the nucleophile. But nucleophilic attack का part I got, but strong base मतलब उसका क्या reasoning. I don't know.
So when the RO minus is attacking, like it's behaving the way it does in the case of secondary or tertiary alkyl halides, is it attacking the carbon or the hydrogen in that case?
Carbon.
Huh?
Which RO minus?
हाँ, RO minus tertiary के case में what is it attacking, carbon or hydrogen?
Hydrogen.
Hydrogen, na? It is capable of taking a hydrogen, taking an H plus, because it's a strong base. Like in that situation, it is behaving as a base rather than a nucleophile. Like when it attacks a carbon, it's a nucleophile. When it takes H plus, bronze state base, like proton
Yeah.
acceptor. So that's what we're saying. So RO minus is also a strong base compared to.
Oh, so there is steric hindrance. So and the main carbon is attached to many other carbons, which is why nucleophilic attack is harder. And because there are more, like, can we say more number of hydrogen? Like, so it will be easier for the strong base to attack, which is why elimination reaction will be possible.
Yes. Yeah. Cool. Other two reactions are pretty straightforward. You don't have mechanisms and all. Huh? What's up?
We'll go back. I didn't finish that. Done.
Okay. Other two methods of preparation.
With the last reason, can you show that?
Yeah. अभी तक क्या कर रहे थे?
Yeah. Done.
Okay. Next. So the next preparation method is also with alkyl halide. So alkyl halide with trisilver oxide. Okay. So this is pretty straightforward. You take an alkyl halide. So again, if you want, so this is a method that you prepare symmetrical ethers with. If you prepare, like if you take different alkyl halides, you will get unsymmetrical ethers, but again, it's a mixture of different unsymmetrical and symmetrical ethers. So preferred method for symmetrical ethers only. Reaction is pretty straightforward. So if you have Rx plus Ag2O, right? So you have two silver atoms. So it's the silver atom taking away the halogen, and the remaining bits kind of get attached with each other. So you get ROR plus 2AgX. Think of it as, what do you call it? Displacement, double displacement reaction. Substitute right. So the oxygen is replacing the halogens here. Silver is taking away the halogens. And then, so this is a method of preparation, but it's not like you're getting ethers from something else. So using Grignard reagent, but this is to prepare higher ethers. Like if you already have smaller ethers, you want to increase the length of carbon chain, then you're going to use this method. Yeah. So Grignard reagent. So this is for preparing higher ethers or increasing the length of the carbon chain. This is also similar to silver oxide wala reaction. So you already start off with an ether, but in one of the carbons, if you substitute a halogen, like wherever you want to attach the carbon chain, that's where you want the halogen to be there. Then treat it with Grignard reagent, RMG, let's say Cl. Then always Mg plus R minus. This takes up the electronegative one. So you get CH3O, CH2R plus MgCl2. So you can see here, basically if you want to increase the length of the carbon chain. So you already started off with a ether which is substituted with a halogen atom, and depending on what carbon chain you want, like what ether you want, you will choose this particular Grignard reagent accordingly. So that gets attached to the carbon from the original ether. Or if you want to make it more accurate, you can use any halogen here, RNGX. Okay. Instead of MgCl2, you get MgClX. Okay. So these are the preparation methods for ethers. Okay. Let me know when you guys are done noting. Then all we have left are the properties. Discuss the physical and chemical properties.
Then chapter done.
Yes, once we're done with the properties chapter. Okay, all organic is going to be like this. Aldehyde ketones is even worse. Amines is like really small. The size
How
of
many organic chapters are there?
2 more. So one is carbonyl group wala thing. So you have aldehydes, ketones, carboxylic acids. And then by the time you get to carboxylic acid, it starts feeling much easier because carboxylic acid is something you're familiar with. And half the properties acids जैसे ही रहेगा. So amines is new, but it's a smaller chapter. It will feel like haloalkanes, haloarenes size. This year chemistry, you guys are lucky. Okay, like from 15 chapters, 5 chapters are like completely deleted only. Whole of P block is deleted. Whole of solid state.
P block would have been better than this.
Huh?
P block would have been better than this. We did that last year also.
P block would have been very, at least in my opinion, would have been very boring.
Yeah,
Would have
but
been very
too
what?
much to remember in.
It's inorganic, no? It's just information. Oh, this is that, this is that, this is this way, this is that way.
But we are used to that sort of, like at least I am used to doing
I'm
that.
not, but I would still choose P block over this chapter.
Organic is like that. Again, these are all again basics. What are you guys planning to do after 12th?
This is the question where none of us like to answer.
No, I don't need an exact thing. Like roughly, are you planning to get into something generic? Like at least you know the subject or the field, right? MBPS versus research versus like something like
That's what we don't know. Yeah, that's what we wish we knew. All we know is bio. Literally the three of us. All we know is bio mein karenge, bas that's it.
I was thinking chemistry, but now this chapter has changed.
chemistry, maybe like
No,
you.
but I do enjoy chemistry. So either bio or chemistry. Not I don't want to go
Yeah.
into medicine. Either of those.
Because organic is, so if you're choosing to go in bio, at least the research side of it, organic is going to help you a lot. Like this, you need to know the basics of.
The fact that we won't have to do physics is
Yeah.
just pushing us to finish it off.
Why?
Yeah, we don't like it at all.
I've observed there are like two kinds of people. People who would like after 12th, after taking PCM or PCB. People who would prefer physics, people who would prefer chemistry.
No,
What
they
about
would
people who prefer neither? Yeah, same.
That's a completely different equation than wouldn't have gotten into science.
And survival.
Hey, bio is there? No, how can you forget
Yeah,
bio?
it's not physics versus
Not.
chemistry, it's physics versus bio. And then chemistry, bichara, is like stuck in the middle. So like I had this sir, I told him, so he used to teach science. Like anytime anyone asked, he used to say, I'm a science teacher. Then I said, sir, what are you specializing? He was like, वैसे तो मैंने physics में masters किया, but ऐसे सब बोलते हैं तो मैं chemistry bio भी बोल देती हूँ.
Yeah.
He used to teach chemistry and then bio. All he used to do, he didn't teach me, he was one of my friends' teachers, but I used to. So he used to just open the bio textbook and he used to just read through that. I was like, how do you learn from it?
Oh man, no. No, but I've observed like if you're more intuitive towards physics, like like if okay, this clicks well, like this thing's well, you'd have trouble with chemistry. And if you have more better intuition towards chemistry, then you'd have trouble with physics. Like I've observed.
The thing is, both of them, science in general is very interesting. That there's no doubt about that. But I find even physics I find interesting. But when it comes to solving questions, it's like I don't want to do that. I could learn and sit in class or whatever. But I don't want to solve questions.
Yeah, like I feel like the practical aspect of physics is much better than what we study. Like numericals and all.
Fortunately, you need that in order to apply that to the practical effects.
If I ever do plan on like studying physics, it will purely be out of interest, just because I want to learn. It would not be because I want a career in that at all.
Understandable. Yeah.
I think right now we're just doing for compulsion. It's not like we actually like the chapter we are doing now, that dual nature wala is pretty interesting. Like it's nice to understand how it actually is happening, but that potential and all, which we are never going to see. Like it's like one charge here, one charge there, axial. It's not making sense. It does make sense, but it's something that we'll never be able to actually see.
Yeah.
Still, for me, physics practicals are more interesting than chemistry practicals. Because in chem lab, we just go and we're like, okay, this is some salt, this salt, that salt, we mix it and we get analysis. This yellow color, brown color. Like we already know what's going to happen. Even in physics, we know, I'm not saying that, but it's still, it's more interesting to see it, like how the circuit is connected and all of that, like the equipment used. It's better, it's nicer to see that, because in chemistry you can't even like everything looks like water. Everything is clear. It's like HCl or HCl. It's all the same.
Yeah, the transparent one, yeah, that's boring. But I have always preferred chemistry ke practicals, because physics ke practicals, like you do it, if it doesn't, you're just operating machines. How is it different from
Yeah, true.
everyday life?
I think I think even we would have thought कि chemistry would with practicals are more nicer, but because even earlier, like at least I have seen like idea है कि chemistry का ऐसा होता है, but physics till now today we haven't really seen कि circuit ऐसा होता है. जैसे हम draw करते paper पे, we actually got to see कि this is what a jockey looks like, or this is a meter bridge. Because till now it was just like, you know, it just wakada tikada lines, but when we actually saw it for the first time, that is why it's more interesting to us.
Going into it, you would imagine that chemistry practicals are more interesting, but then when we go in the lab, it's like all the reactions are written on the board. We know कि ये mix करेंगे तो यही मिलेगा, तो उसमें कुछ ऐसा
That novelty is gone. Huh? You'd have seen it in like videos and things. It's told to you already. So the best thing about chemistry practicals is, I don't know if you guys have it right now or not. One was like golden rain wala thing. Again, I forget kiska test tha wo, but basically like test tube mein you can see there's like a golden rain inside the test tube. It's like the coolest thing ever. And the other one was golden spangles or something, and the other one was brown ring test, because it was all hyped up. It's very difficult. You need to be very careful and all that. So it felt nice to get that brown ring.
But brown ring test is actually very cool. Like we did it in 9th, and like a teacher did it very carefully. We were not allowed to do, but we saw it like in front. She did it like side se edge to support. It was very nice to see.
Brown ring test, you have it in like right now this year. I don't know if you have those that practicals or not. Like in theory, may to definitely have. So you have that. Okay, so back to ether. There's like mainly just one major reaction. It's just okay, different ethers, different cases. Like that's what we have it. Achha, before reactions, we need to discuss physical properties, na? Okay, physical properties. Same thing. Like so ether may, okay, we're not going to talk about appearance again. It's like colorless, odorless, like the usual thing. But the thing that affects the solubility, boiling point, melting point, and all of that, the first thing we'll talk about is the dipole moment, the polarity. So what do you think about ethers may polarity?
In symmetrical ethers, I mean, unless it's like a major difference between R and R dash, it's non-polar.
Okay, before we discuss, what would be the shape of ether, like R dash at oxygen? Do you think it's bent? Is it a straight line shape? Kya hoga?
It will be bent, right?
Yeah, because oxygen has lone pairs, so there'll be repulsion.
Okay, tetrahedron geometry, jisme two of them are lone pairs, so it's going to be bent. Okay. Whether it's symmetrical or asymmetrical, it's attached to carbon only on both ends. Okay. So considering all of this, like what do you think the dipole moment or the polarity will be? Is it a polar?
It will be polar.
Okay. And what would be the scale of the polarity?
What does that mean? Like
Like is it extremely polar like alcohols, less polar than that?
I mean, oxygen is pretty electronegative and it will take the electrons from both the R's and the resultant will be. But
I don't think it will be a lot like large polarity.
Okay. Yes, mera sunscreen.
compared to carbon, oxygen is not like there's not much difference between them. So there will be polarity, but it won't be zyada.
Okay. So yeah, Smera,
Yeah.
Sanskriti.
Even I think it will be polar,
Yeah.
but not that much.
It is polar. It is not non-polar, but yeah, very less polarity. So the polarity is very less that ether is used as a solvent for a lot of organic reactions. So where you prefer not having so much of polarity. इसलिए Grignard reagent के साथ reactions and all, if you use properly polar solvents like water and all that, the reactions gonna go in a completely different way. Like Grignard reagents gonna take H plus from there, gonna get alkanes. But dry ether is not polar enough to trigger that. So you end up using this. Okay. Next, talk about boiling points. Okay, so first, like the usual thing stands, as the molecular mass increases, boiling point increases. That is the trend. Let's just put that point there.
Miss, what is the reason for very less polarity?
It's again, the only polarity is because of the shape, comes from oxygen and the fact that it's tetrahedral shape. As Kaveri said, like net dipolarity will be like this. Next dipole moment. But on both sides, it is carbon only, right? Like if one side is oxygen, it will be uneven, kind of contribute to that. But because it's carbon on both sides, it's very less. And the rest of the molecule is all tetrahedral hydrocarbon only, which is mainly non-polar. It gets cancelled from all this.
But like,
Alcohol,
does it need
yeah.
to?
So
Sorry.
the thing when it comes to alcohol, it is unsymmetrical. Like यहाँ पे carbon oxygen pulls on it, oxygen hydrogen है, which along with the dipole moment coming out of this, you also have hydrogen bonding involved. So that makes alcohol extremely polar, which is why it is capable of dissolving in water and all of that. But ethers are not the case. You have a lot of hydrophobic, what do you call it? Hydrophobic parts of the molecule. Like both sides, there are hydrocarbons only, which makes it practically non-polar. Whatever little polarity is there, that comes out of the shape of this thing. Okay. Next, boiling point compared to alcohols. So ethers ka boiling point will be greater or lesser? Very related to what we discussed right now.
Lesser.
So यहाँ पे polarity, like you have a dipole moment plus hydrogen bonding. So ether में there is no hydrogen bonding.
There's no edge, yeah. There's no
Yeah,
edge.
electropositive edge. Not electropositive, but yeah, like edge with the delta positive है ही नहीं. So no chance of this thing. So ethers का boiling point will be lesser than alcohols. What about compared to alkanes? Alkenes versus ether. Alkanes again of comparable molecular mass. We're not having something that's so strong.
There is very less polarity, and in alkanes also there's not like a significant difference. So
Yes. Yeah. So with alkanes, almost comparable. Ethers have slightly higher boiling point compared to alkanes. And whatever difference is there, you can see that like one possibility is that there's oxygen, which is different from carbon, hydrogen, thoda sa mass difference hoga. And secondly, there is very less polarity, but definitely there compared to alkanes. Alkanes may zero polarity. So,
Miss,
hmm?
I have a question, but in R and R or R dash, can there be alkenes?
That possibility is definitely there. You can have something like CH2 double bond, CH, CH2O, CH3.
हो सकता है ना?
Uh-huh.
Because when
But
we
then we
like
always
write
say alkoxy, sorry, but we always say alkoxy alkane, no? So
alkane, yeah, I was gonna say this.
So that's the most common ether, like, but this is not like an impossible compound. Possibility to hai. Of course, it's going to have completely different set of properties and everything, considering double bond bhi hai. Like it's not going to behave in the same way as your normal ethanes.
yeah, obviously we know that this exists, but like, is it an ether?
Is it a?
Will it be called an ether then?
It is a type of ether, क्योंकि alkoxy group तो है, but there is also an alkene. So so mostly like when we talk about boiling point, we majorly compare it with alcohols because functional group structure wise they're very similar. Like the only difference is यहाँ पे hydrocarbon group है, यहाँ पे hydrogen. So there's that comparison. And with alkanes, again, like majorly hydrocarbons except there's one oxygen in the ring. So there's like a comparison with alkanes. And next we talk about solubility.
What is DM?
Dipole moment, I just shortened it. It's not like a formal, like you won't come across this anywhere. I just shortened it here. Okay, considering all of this, yeah.
Why does ether have slightly higher boiling point?
So there's a little bit of polarity in ether, which won't be there in alkanes. And secondly, oxygen instead of carbon, that also contributes that difference in molecular mass. Won't be exact same.
Okay, so this is a dumb question, but why does it have a higher boiling point? Because it's more polar.
Polarity, so more polar matlab more attractive forces, right? So higher boiling point, you need slightly more energy to vaporize ethers compared to alkanes. So they are mostly comparable, it's just slightly higher. Like, the difference is not that significant. Yahan pe this difference is quite significant, much higher than ethers. Next, solubility. What do you guys think about the solubility?
Soluble in non-polar solvent.
Yeah, as all organic. What about solubility in water?
It has very less polarity. So water
I-
might be able,
So
yeah, it
the
must be
Let's put
soluble.
it here. So ether hai.
bond between the
I think it will be soluble because there could
Even
be
I
H
think.
bonding.
So within ethers, there is no H bonding, but when you mix it in water, the oxygen is fully capable of, having that H bonding with hydrogen from water. So when we talk about solubility, it is similar to that of alcohols of the same molecular mass.
ma'am, what is the type of bond in ethers? Like
Covalent.
no, like the forces.
So you have
Like haloalkane is dipole dipole. So what is that bond?
इधर भी dipole dipole ही होगा. Just that it's not as strong as you might have, because again, species electronic.
That also adds to it, right? That it will be easier to break the bond between the
Yeah, I was
ether also, and then plus the edge bond.
In
yeah,
which,
because in solubility of haloalkanes, as a give reason, the reasoning that we wrote was that water isn't able to break, like the solvent and solute reactions are just as strong. So water is not able to break the bonds between haloalkanes. That is why they're very slightly soluble. So over here also, is there any case where, because of lesser polarity, water is able to break those bonds and that is why it is soluble, other than the H bonding criteria?
yeah, like H bonding matlab water is able to form bonds with the
Edge bonding
oxygen.
is that only na कि between the ether and water, like the solute solvent interactions are stronger than solute and water. Like it's able
Not
to
stronger, comparable. Stronger,
Stronger
the
matlab
energy.
dissociate ही हो जाए.
almost
Compared.
similar.
What
Comparable.
was what was written in the haloalkane wala thing?
That it is comparable. Matlab, just as strong as the original one.
Okay, either similar to alcohols uh, with the same molecular mass.
And ma'am, another
Miss?
question. In this, for solubility, we always mention energy. So by energy, are we talking about the bond enthalpy between solute, solvent, and then the energy that is between the solute to solvent that has to overcome the energy between the solute, solvent, right? So what is that
Yes.
energy? Like, what is the energy that is being in the formation of those bonds? What is the energy?
That is the energy. So that's not bond enthalpy. Bond enthalpy is
Bond enthalpy is to break the bond. That is for water and haloalkane.
within that itself. So don't talk about bond enthalpy in that context. But energy. So anytime you have so again, like you guys did electric potential and all of that, right? So when you have two charges interacting, unme there is like a potential between them, which means there is also energy involved between them, that potential energy involved with those interaction of charges. So that's what we talk about in all of these situations wherever energy is involved. Like even within a covalent bond, what is covalent bond? It's like both the atoms are coming close enough that um, their electron clouds are kind of merging. They're overcoming the repulsion. That's why if they're any closer, the repulsive forces get stronger. That's why it's like it's forming at a specific distance for any two atoms, right? So there also we talk about, if you remember chemical bonding में that graph, we talk about the potential energies there. So whenever there's like two charges interacting, be it lone pair of electrons or within an atom
But
electrons.
इसमें potential energy कहाँ से आया?
हाँ?
इसमें potential energy कहाँ से आया?
Between charges.
Potential energy
I'm so
between
confused.
yeah.
Okay, this is like, let's finish off solubility, then we'll elaborate. I'll like talk about that. Okay. So like solubility is similar to alcohol. So if you look at diethyl ether, uska solubility will be similar to butanol ka this thing. So dimethyl ether ka solubility will be similar to ethyl alcohol ka this thing. So following that pattern, so the first 4 members are like miscible in water, but as the carbon chain increases, the solubility will start decreasing by a lot. First 4 members are miscible, matlab they can dissolve in water, they mix up in water.
First 4 members, why only 4?
Because they're the smallest. Like as it starts increasing, the extent to which they are able to dissolve starts decreasing.
Earlier, whenever we wrote give reason, like up till 10, whenever we wrote give reasons about why water is able to dissolve most of the substances, we wrote that water has a high dielectric constant, which is why it is able to, like break through the forces and Vaisa. So what has dielectric constant got to do with it?
Oh, that's something that I haven't heard in a long time. Love the exact definition. Dielectric constant, you must have studied in physics, no?
Physics, yeah, we did, which was like related to permittivity of free space and basically permittivity. But I don't know, because we always wrote that water has a high dielectric constant, which is why it is able to overcome those intermolecular forces of attraction between the molecules. See, I have it by heart. That's how many times we've written. So this is the reasoning we wrote always for why something was
What are you
soluble in
talking
water.
about? I got disconnected.
So
Why water is able to dissolve a lot of substances. As a give reason, we used to write that water has a high dielectric constant, which is why it is able to break through the intermolecular forces and dissolve those certain substances. So I asked what it's got to do with dielectric constant.
Okay.
okay. So what I'm reading here is dielectric constant, it's the expression of the extent to which a material concentrates electric flux. So as the dielectric constant increases, the electric flux density increases. So here also it's related to
Is it?
electric
And like electric
charges.
Yeah.
So charges, where do they come from? From like everything to do with water. Like oxygen has that lone pair of electrons, it's pulling on the electrons. Like you very clearly have 2 different oppositely charged this thing, right? So
Yeah.
I guess this is another way of saying water has a high polarity.
Yeah, maybe, but doesn't seem so convincing.
So high polarity, matlab, like in chemistry, when we talk about polarity of molecules, that's exactly what we're talking about, the separation of charges, the fact that we have like
Yeah.
positive charge and negative charge. And when I'm reading about dielectric constant, that's what it's dealing with. The extent to which a material concentrates electric flux.
Flux. Yeah.
Yeah. The main difference is that when we talk about all these quantities in chemistry, they're at a micro level, like between 2 molecules, between 2 atoms, things like that. What you guys are studying in physics is at a macro level, like things that you can see between 2 metallic plates and things like that.
Yeah.
But otherwise, the principles of it will always remain the same. Like charges are charges.
So
Whether,
maybe it's like high polarity
yes,
there.
different way of saying high polarity. Yeah. Yeah, just different terms used in different contexts, depending on what you're using it for and what is the desired outcome for that. Okay. All right, now talking about energy, like chemistry, we always talk about energy. Energy is like everywhere. When you break bonds, sometimes you need energy to break bonds, sometimes a lot of energy is given out when you break bonds and all of that. So energy that we talk about is, so every time there is interaction, at least when we're talking about like whatever uh, chemistry related stuff, every time there is interaction of charges, there is a potential associated with it. It is the same thing what you guys studied in electricity related chapters like electrostatic potential and all. So along with the potential, you would have talked about like work done in order to move a particular charge against a field or like uh, within a field, right? So to do that work, you need some energy. Yeah. So that's what it is related to. Like, how can I put this in very, very simple, basic terms? Is again, let's come back to playing with magnets. So when you wanted to push two magnets that are repelling against each other or pull apart magnets that are attracting against each other, मतलब उन दोनों के बीच में there's forces involved, right? Attractive forces or repulsive forces. And if you want to act against those forces, you need to put in energy for it, right? So that energy, like, because there is a potential created between both of these to do some sort of work, some sort of action, potential to expend that energy. So that particular energy, we call it potential energy. That's why you have gravitational potential, electrostatic potential. You have like magnetism के साथ related भी, you have potential related to that. Even within mechanics, spring, like when you compress a spring, there is potential for that spring to do work, like oppose against that compressive forces and push against that. So that there you have potential energy. So you just scale it down to atomic level. So if you have two electrons coming close to each other, because of that repulsive forces between them, you have potential energy created. If you have attractive forces, like you need to expend energy to separate them out. So there's that potential energy created. Yeah, so that's like the kind of energy we talk about in all these cases. Excuse me. Okay. So we ready to resume, guys? Smera, Kaveri, Sia?
Yes, ma'am.
Yes.
Chemical properties. So alcohols may we had cleavage of OH bond and CO bond. Two different types of bonds are there. इसमें we just have carbon or oxygen के bond. So we just have cleavage of CO bond. That's the only bond that is there in ethers because it's ROR dash. So we don't have a lot of reactions associated with ethers because they are one of the least reactive substances among organic compounds, among all functional groups. And that is one of the major reasons why we use ethers as a medium for a lot of organic reactions. Like if you don't want polar solvent, if you don't want to do it in water, dry ether is what you would use. Okay. So ethers are one of the least reactive substances among all functional groups. So the only substances that are less reactive are, so they are better than hydrocarbons like alkanes, not even alkenes, alkynes. They're only better than alkanes, cycloalkanes, and fluorocarbons.
acetone a polar solvent or non-polar?
Acetone, again, acetone is much lower in.
Dissolves both.
Yeah.
Yeah, it does, right? Acetone will dissolve both
Acetone is
polar
See,
and
acetone has polarity, but again, it depends on the context. So if you compare it to something like something with acidic medium, basic medium with water and all that, definitely less polar than that. But it is also more polar than alkanes and ethers.
So no, but like how can it dissolve both?
How can it dissolve both, matlab?
Kaveri said it dissolves both.
yeah, both polar and non-polar solutes.
Again, from what we've learned here, polarity is not like 0, 1, black or white. It depends कि कितना dipole moment है. If the dipole moment is high, it's properly polar, highly polar. If it is very low, negligible, like net zero,
Non-polar.
zero, it is non-polar. But when it is very low, so like on a spectrum, right? So depending on where it is, it will it would have the capability of dissolving both like polar substances and non-polar substances. Like it is hydrophobic enough to dissolve non-polar substance like organic substances, but that dipole moment is just enough to dissolve like polar substances also. Right. So coming back to ether, yes. So because they are least reactive, only better than alkanes, cycloalkanes, and fluorocarbons, so they are used as a reaction medium. Used as solvents for reaction. Okay. So that said, ethers are still capable of reactions. They're not completely inert. The only reaction that is well known that we're going to study now is reactions with HX. So under drastic conditions, again, like high temperature, specific solvents, things like that, reacts. So basically the carbon oxygen bond is broken with HX. Hydrohaloacids, HCl, HBr. Yeah. So the basic, like the mechanism of the reactions will change and the products that are formed will depend on what ether you're using. But the basic reaction is that you get an alcohol and an alkyl halide. Okay, so you have, so we'll start off with symmetricals like simple ethers because they're same on both sides. When we start talking about complex ether, like unsymmetrical ethers, then we look at, okay, what is going to form alcohol, what is going to form alkyl halide. There's some differences there. But with this, because R is same on both sides, the same product, like, it's less complicated. So let either of these are broken. Here bond, like this bond is broken. So hydrogen will go towards oxygen and X will go towards R. So you always get ROH plus RX. And so once this reaction takes place, depending on how much HX you take, there is one more reaction further. If you recall, alcohols react with HX to give you more alkyl halide plus water. So with this, the ether is completely broken down. And special case, if you take aryl ethers, no matter what this R may be, you get the same products always, which is phenol plus RX. So this is one of the methods of preparation of phenol, that you take any alkoxybenzene, treat it with HX. You always get phenol, and the R goes off as HX. Can you guess the reason for this?
Reason. Okay. No.
Okay, note it down, like look at what's happening here and see if you can figure out the reason. Think about it, I'll just be back. Yeah, any ideas? This is something we discuss always when there's a benzene ring in question. That's your hint.
Resonance.
Partial double bond characteristics.
Yes, that's it. So always like lone pair on oxygen, this is involved in resonance. So this particular CO bond is much strong. Like it's not, you can't break this that easily. So always the cleavage happens on this side.
Ma'am, underrated question, but not really. Plus R and minus R plus R is where the ring is pulling the electrons towards itself, right?
Yes, electrons.
So
are-
you remember that chlorobenzene wala question I had sent about S character and R. So in that they've written minus R effect. So shouldn't it be plus R instead of that? Where since the
Exactly.
carbon
Yeah. No.
the
So
car asked why
it is plus R and minus I. So
no,
plus R
they've written minus R effect.
minus R नहीं होगा, because chlorine के lone pair of electrons are getting in there. It would be minus I effect because chlorine is electronegative and it pulls on the electrons.
But that is being overcome by the S character and the plus R effect, which is why
Yeah.
chlorobenzene is
Orthopara. So this is because, like always, like why is this the case? Because the CO bond between the phenol, like the benzene ring, like the phenyl carbon, benzene and oxygen is strong. And why is it strong? Because resonance and has a partial double bond characteristic.
So what did you say about the minus R and plus I? Can you please repeat?
It's a specific case, like Kaveri had sent a question. So chlorobenzene ke case mein, like, I've forgotten what the question is, but what happens in chlorobenzene? Like, why is it? I think it's why is it orthopara
It
directing?
knows the question. Chlorobenzene less polar than cyclohexyl.
Compared to cyclohexane. Oh yeah, we had also discussed that.
Yeah.
So yeah, like chlorobenzene, because chlorine is adding electrons into the ring, like ये पूरा resonance में आ रहा है ना, so that contributes to plus R effect. That is plus R, not minus R. The thing that nitro group does, where it pulls electron from the ring, जब इस direction में जा रहा है, that would be minus R.
I thought minus like inductive effect was only in straight chains.
Inductive effect is where it pulls on the electron. Like, maybe also.
So inductive effect,
Minus-
we said that chlorine is more electronegative. We are implying that inductive effect will happen, right?
Yeah.
Minus I is when it. What was minus I?
Inductive effect.
But plus.
Plus,
What is
when
the-
it's pushing electrons, plus is always adding electrons, minus is always taking away electrons.
When
So-
does plus I happen?
Alkyl groups.
Yeah, but
when
like
it is minus R, that time there is plus I, na? And when there is minus plus R, there is
No.
minus I effect. I thought it always went hand.
question, just in this question, there is chlorobenzene. So we are saying that there is minus I effect because chlorine is more electronegative. So it has a tendency to pull electrons towards itself. But there is also S character greater in the carbon of the benzene.
Yeah.
And there is plus R effect. So that is more than that.
That I know, yeah. Just only in this case. Yeah.
Just in this case, otherwise it's not a combination of.
No. Plus R minus R is a completely different thing. Plus I minus I is a completely different thing.
But ma'am, plus I will happen. Okay, alkyl groups are pulling, but when will that happen? Like, how can anything be like, I don't know, like what is an example of plus I effect compound?
So wherever you have electron donating groups, that contributes to plus I effect. So if you find electron donating groups in an aliphatic, like in a straight chain, that's plus I effect.
And can plus I effect happen in benzene, like when something is attached to the benzene?
Yeah. So
But it won't. Yeah, it can happen if it's electron donating.
directing plus R plus I goes like hand in hand pushing electron.
But ma'am, when we say halogens ke liye, halogens, I know it's an exception key. They are when they are with the benzene ring, they are electron donating, but otherwise they're electron withdrawing. So if they are electron donating, then how can we
So
say that
that
there
is, like I said, that electron, like put them under electron donating because it's easier to remember ki okay, so fir they are orthopara directing.
so because they are giving the electrons to the
Yes.
ring. So then how can we say minus I effect hoga?
Because by nature they are electronegative, like they have a tendency to pull on electrons, right? So by default,
So they still have electronegativity, but just that when they are with the ring, they have a tendency to give electrons to the ring.
that's purely because they have those lone pair of electrons. Nahi to they'll just keep pulling on electrons. Okay, so this
So
was
even in the but even in the chlorobenzene one, it will have partial double bond characteristic.
Yeah.
na?
okay. So this is what, like with symmetrical ethers, it is pretty straightforward. Kyunki it doesn't matter whether bond breaks on this side or this side, you get the same compounds because you have the same alkyl groups. Pretty straightforward. Okay. Phenol, like anisole ke case mein, not just anisole, but when you have a phenoxy group, yeah, like over here is always where the bond breaks. You always get phenol plus alkyl halide. Now coming to unsymmetrical ethers. So how do you predict the products formed in the case of unsymmetrical ethers? So if you have R dash, same reaction, and you make it react with HX, what are the products here? So that depends on R and R dash. So the alkyl group, so always the halide is formed, like Rx is formed with the less bulky group, the smaller group, and the alcohol is always formed with the more bulky group. So the cleavage happens on the side where there are lesser number of carbon atoms. Okay, like for example, suppose we have CH3O C2H5 plus HCl. What are the products formed here?
CH3Cl and C2H5OH.
Yes. Yeah, the smaller one, less bulky, lesser number of carbon atoms, will always form the alkyl halide. More bulky will form the alcohol. So why is this the case? Like we look at the mechanism. Actually, I'll do the mechanism next step. Like just note this down. Note down this note. Key less bulky is this thing, more bulky is alcohol. Once you're done with this, let me know. We'll start with the mechanism. Sanskriti done. So Kaveri, Sia, you know.
Yes.
Okay, so mechanism, step one is always, as always, you have protonation. So basically HX splits into H plus and X minus. So protonation, so this particular H plus, so there's protons in the mix. So let's say CH3, O.
Miss, where is the mechanism in the textbook?
Yeah, I don't know. I found out and I like noted this down. Just keep it for information in case you have a doubt, in case you get a question. It's quite simple. It's just the difference between primary and tertiary.
Oh yeah, no, there is. It's in the box. That's it. Yeah, sorry.
So you have this. Step one is always protonation. So H plus, like यहाँ पे जो है, that H plus attacks the oxygen. So here I'm putting it R dash because I'll split this mechanism like depending on what R dash is. Okay, so you get CH3O, H forms a bond, so this will get a positive charge and rest of it remains the same. And X minus तो है उधर ही. It is 2 steps. So once this is done, step 2, either you can write down one after the other or you can divide the page depending on how your notes is. But here's where it splits depending on what R dash is. So if the more like if the one of the groups is if R dash is primary, then you have an SN2 attack. And if R dash is tertiary, then you have SN1 attack. And यहाँ पे SN2, SN1, the nucleophile is X minus, halide ion जो भी है solution में.
Yes.
Hmm?
A bit unrelated, but since here there is HX, there was in haloalkanes, there was a statement that I wrote was that iodine is best leaving group. Means what?
So when you have Rx, the easiest bond to break is iodine. Like the one that leaves most easily is iodine
Because it's larger size.
compared to chlorine bromine.
Yeah.
Okay. So getting back to this primary है ना, so here's where I'll take like a specific example. So if we have CH3O and C2H5, oh, should have planned this. So SN2 attack, just like we saw earlier, the nucleophile like X minus, यहाँ पे HP है ना, that's what we had. So as the bond breaks, this bond is created. So what you get is you have, no, it's easier for this one to leave. This is where we are. This will attack this while this goes here. So you have CH3. On one side, you have X minus, which is attacking, like which is trying to form a bond. On the other side, you have the oxygen and the rest of it trying to leave. Okay, so this is the intermediate that's formed. So it's pulling these electrons. This is trying to form a bond with this. So your final product, like once the bonds break and all of this gets settled, you have CH3X plus CH2, CH3, CH2OH.
If the how is there a plus sign even in the intermediate?
मतलब
वो arrow से इलेक्ट्रॉन कहाँ से आ रहा है?
this bond, like C के साथ जो bond है, oxygen is pulling on these electrons. So this is like during the process, like while oxygen is taking
अच्छा, oh, okay.
electron, this is trying to form a bond with this. Like both happen simultaneously.
Yeah.
Okay. Now coming to SN1 attack. So this happens when there's a tertiary carbon present. So SN1, if you remember, it's like a two-step thing. पहले carbocation form होगा, उसके बाद the nucleophile comes and attaches itself there. So we are starting off with this. We have CH3 OH with a positive charge, and here पे tertiary this thing is there. So it's easier for the carbocation to form. So this bond breaks first. So this will give you so CH3 OH plus CH3 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 plus. Okay. What we've written earlier is wrong. Okay. So just make a little correction. क्योंकि tertiary के case में this gets interchanged. This we need to correct. But otherwise, yeah. Then nucleophile comes and attacks this. So we have CH3, 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 carbocation plus X minus gives our alkyl halide. Why was this written? Where did I get it from? Let me know when you've finished noting down the mechanism. There's a correction to be made.
After that, in SN1, after the first line, what do I have to write next? Like it's confusing.
This
What
one,
night?
ये वाला part. Oh, so यहाँ पे carbocation form हुआ है ना? So the X minus, the nucleophile that's there, that bonds with the carbocation. So this plus and this minus get together to give you your alkyl halide, tertiary alkyl halide. Shall I take it to the next page? Like if you all have done it till here, I'll write it clearly.
I didn't. How did the? अच्छा, you wrote it as CH3 3.
क्योंकि space
उसके बाद और एक C किधर? अच्छा, oh that C.
all of you done?
Are you going to write it on the next page?
I can if you want. Yes. यहाँ तक लिख लिया ना?
Yeah.
Okay, so last step is this is what is formed end of that previous step. CH3 tertiary, and then you have a carbocation. Yeah, like this combines with the halide ion gives you your halide. Okay, so make this correction here. So what is written here is wrong, not always. So Rx and ROH depends on what groups are present here. So this is the case with primary, when both the groups are primary. But if one of them is tertiary, then that tertiary will always form alkyl halide. So this will depend on whether it's SN1 or SN2. So when both are primary, then for tertiary, like, or let's put it this way. If R dash is tertiary, then R dash X is formed and ROH is formed. Because always tertiary will form a carbocation, so हमेशा the negatively charged thing will go with the carbocation. Okay. Kaveri, Sanskriti.
If secondary, then
If it is secondary, then like ideally it would depend on the reaction conditions. Like it's the same with our nucleophilic substitution also. If the medium is polar, then carbocation will be formed. If the medium is non-polar, then SN2 is favored. Also depends on also
yeah,
depends on steric hindrance conditions. So it's like a case-to-case basis for the secondary. You need to check.
and in tertiary, R dash, as in you're referring to the more bulky.
Yeah.
How will it form Rx if R dash is more bulky? How will it form R dash X?
We saw it, na? Kyunki tertiary carbocation is more stable. So when this bond breaks, it would prefer forming a tertiary carbocation as opposed to primary. Or even if you're comparing primary versus tertiary versus secondary, tertiary will be preferred. So that's how the bond break happens.
Wait, but for 3-degree, where is the alcohol formed?
When this bond breaks, CH3OH form hua hai na? All of this is one group. Isliye we got our CH3OH. Let me erase.
So that is R, right? Not Rx.
Huh.
Sorry, that is R, right? Not R dash.
Yeah.
Yeah, so then it should be Rx and R dash OH.
How does that make a difference? If you take R,
Yeah,
it depends
then-
na ki kya le rahe hai.
Like, can you show the one that you wrote if one of them is tertiary? Yeah, so if R dash is tertiary, then how would you get R dash X? That's what I'm asking.
Tertiary, like whichever is tertiary, that will form a carbocation.
Why can't you get R dash X? If it's
The
It should
more
be R
bulky
dash,
one,
yeah, R dash OH, right? Because more bulky goes to OH.
but that is for primary.
That's why I asked you to
That's what
correct
she's
it.
saying
That's
na.
why
No, that is Only for primary.
Yes, when
The
both
more
are
bulky is also for primary.
primary, this will be the case. The less bulky will be Rx and the more bulky one will be ROH. And the reason for that is it's following SN1. So the attack will happen where there is more space. So less bulky one will form your Rx, alkyl halide. So this will change with tertiary. That's why I made the correction. That's why I wrote it in red. So make sure you note it correct.
Can you like show this thing that you wrote R dash X plus ROH in the equation that you gave us example? Like what is R dash, what is R?
That's why I took this example. Like
You can take either.
I didn't get you what?
Okay, so you have written if R dash is tertiary. So can you like show that in this example?
Here.
Yeah. So R dash would be which part? The tertiary one, right? That C where, yeah. So that one is getting attached to X.
Yeah.
Yeah, okay.
It's always important to follow mechanisms. Primary के case में वो हो रहा है, tertiary में it's different. Okay, so that's the main thing. And going one step further, when the HX is present in excess. So symmetrical के case में भी we discussed this. When you have excess of the HX, the alcohol is getting converted to alkyl halide. Same thing will happen here also. And at higher temperature, we have CH3, CH2OH. Let's suppose we have the alcohol formed. This lone pair will attack this oxygen. This will take on this thing. So this is going to form. Same mechanism like what you guys learned when we were like looking at this thing. So this will take on a pair of electrons and X minus will attack the carbon. So this in turn will produce CH3, C seems to be.
Yes.
Hmm.
In the textbook, there is this line, therefore attack by I minus ion breaks the OCH3 bond to form CH3I, and phenols do not further give halides because sp2 hybridized carbon of phenol cannot undergo nucleophilic substitution reaction needed for the conversion to halide. Means what?
Okay, the first part of that statement is describing this process. The I minus, so in like they've taken specifically iodide ion instead of X minus. So that's attacking the CH3, which breaks the bond with oxygen over here.
Yeah.
Okay, the next part of it is talking about, and maybe it's talking about this also, like HX. So next part of it is talking about when you have an aryl ether involved, like this particular case. So symmetrical or unsymmetrical, दोनों cases में, the alcohol that is formed is being converted into alkyl halide. But that will not happen, like excess HX use करने पे, this conversion will not happen with phenol because this bond is stronger.
When in the first reaction, the alcohol will be converted to alkyl halide. No, that only. This, yeah, isme the one which you underlined RX in blue, in that only excess HX, yeah.
Yeah, you need that HX, extra HX continue the reaction now. This is like excess HX case.
Okay.
So this excess HX, like no matter, even if you have excess HX, this conversion will not happen. Like phenol will remain as phenol because this bond is quite strong. Yeah, same thing. Excess HX case mein, you get the alkyl halide from both the alkyl groups. This gets converted. So whenever you have questions related to this, that's something that you need to pay attention, whether you have like excess HI or if that excess is not mentioned, then you get alcohol plus alkyl halide. That's the thing. And so this is for regular like normal ethers with alkyl groups. Anisole specifically has special reactions associated with. Oh, not done yet. Okay.
Now only electrophilic is left, na? Halogenation, nitration, Friedel.
What else? Halogenation.
Friedel crafts, hydrogenation, nitration. Yeah. There's no sulfonation.
Why you want?
I mean, it's not very difficult to predict sulfonation के साथ क्या product आएगा. Like any
How
electrophilic,
would you
get the same thing.
Done.
Orthoparameters.
How would you get a sulfonated product with ether?
Same way you get sulfonation product with other sulfonation reactions.
So like nitration in place of NO2, there would be SO3H.
Correct. So electrophilic substitution, this is specific only for anisole. So what do you think? What sort of products will you get electrophilic substitution with anisole? Orthopara, meta?
Orthopara.
Orthopara. So generally OR is orthopara directing. So anisole के साथ जो भी reactions है, it's all orthopara directing. In this case, like there is a clear distinction. Like पहले usually orthopara दोनों products produce हो रहे हैं. But in the case of anisole, clear distinction where para is a major product and ortho is a minor product. Definitely a lot more than meta. Like meta is less than 2%, less than 3%. Ortho is minor enough that it's like between ortho and para, like para is like almost 90% and ortho is like 10%. A lot more than meta, but like a lot less than para. Just like with phenol, okay, like we'll talk about individual cases. First one, we have halogenation. So halogenation के लिए reagents क्या चाहिए?
Bromine. Like for brom. Bromination के लिए bromine.
Bromination.
Is it bromine water here also or?
No, like again, remember phenol is a lot more polar than ether. but definitely more than benzene. So you don't need a Lewis acid, but you still need something like acetic acid. Roman water also works, yes.
Because methoxy group is highly activating. No?
Yes.
That is why we don't need.
You don't need a Lewis acid, but yeah, Roman water, ethanoic acid, that works.
मतलब bromine water or methanoic acid is fine, no?
Yeah.
Or only, yeah.
So auto para directing, you can predict the products.
When is this chapter going to end?
Last set of reactions, no? And this is not even heavy because you've done electrophilic substitutions enough times.
No, it's still heavy.
This is something that you guys can start answering on your own. You already know it's orthopara directing. You already know what reagents are used. All I have to do is like just tell you guys like the minor this thing changes, tweaks. Okay, so I won't be writing the entire reactions for Friedel-Crafts reaction and nitration, but I will definitely ask you the reagents used for it. So Friedel-Crafts, there are two types of reactions. We have Friedel-Crafts acylation and we have alkylation. So we'll talk about alkylation first. What reagent do you use for alkylation?
Anhydrous AlCl.
Just that? That's a helper for your actual reagent.
CS2.
That's a medium. Alkylation, कहाँ से मिलेगा ये alkyl group?
अच्छा वो CH3Cl.
हाँ, CH3Cl in the presence of anhydrous AlCl3. Write it as RCl or RX because
Yeah, because it could
then
be
ask
CL.
what alkyl group you're putting there. Next, acylation के लिए Friedel-Crafts acylation. Yeah.
OCl. ROCl. Something
Close.
like that.
Something like that, yes.
COCl?
So this is acyl group. C double bond O attach karna is acylation. Specifically, like if you talk about CH3, this is acylation. Introducing this group, reagent you use is Cl and anhydrous AlCl.
There was some reasoning on Suna why CS2 is used somewhere, carbon disulfide. I don't remember the exact thing, but somewhere there was a mention of why carbon disulfide is used, probably in the previous chapters. But I don't really
Sulfide is
remember.
used in lots of cases. Yeah, need context. That's also a popular medium, just like dry ether. And then nitration. Smera, what reagents do you use for nitration? Smera?
Yes, ma'am.
Yeah. Nitration के लिए what do you use?
HNO3 and the other one was H2SO4.
Absolutely. So concentrated HNO3 in the presence of concentrated H2SO4. So H2SO4 is required to produce the nitro group, and the nitro group goes and gets itself attached here. Okay. And that's basically it. Ether was much smaller, like you only have one major big reaction, and you had multiple cases in that reaction because depending on what alkyl groups are attached. And then you have your usual electrophilic substitution. This electrophilic substitution you will have in every single chapter because you have an aromatic ring, electrophilic substitution to by. Okay, so guys, yesterday and today, whatever we did, so like write down these reactions. Don't just write down shorthand what I mentioned here. I did not write the reactions on the board because yeah, you should be familiar with it because we've done this enough times. Recently, yesterday only we did it in phenol's case also. So complete the reaction the way bromination ke liye I've written. Write the reaction for alkylation, acylation, and nitration also. And scan and send your notes. This is the end of the chapter. So pura yesterday and today, whatever we did, send the PDF of your notes today.
Ma'am,
Yeah.
what about the test thing?
Testing schedule, right? Yeah. So I'll be sending it by before 7:30 today. Working it out. Just need to put in the schedule.